those elements are important. Sometimes we're building up models out of these. At a practical level, they help us put together a model into pieces, put together a model with these sort of competing risks, put together models with these sort of stages here. Now, you'll notice that this diagram here includes an aging chain. What else does it include? Competing risks as well. So very often you'll have kind of both in the mix. But really those are kind of fundamental pieces out of which we'll build up the model for many model basics. Now, we're going to be seeing very soon now discussion of some other features that will make the dynamics of these models much more interesting and textured. We've kind of been building up the basic building blocks, which are fairly straightforward sort of dynamics associated with them. There's some subtleties, but they're fairly straightforward. We're going to be looking, probably next lecture, at nonlinear dynamics. This is where things get really, really interesting and non-obvious. And this is where these skills that you've learned in this lecture and the last few lectures on building blocks, etc., will come in handy, not only in building up a model, but in analyzing what is going on. Why is it behaving in a certain way? Even though it's not linear, we'll be able to use these tools of reasoning about equilibrium and what that means about stocks, about the flows, etc., to kind of understand what's and appreciate what's going on at a deeper level. So we're going to take a look at some nonlinear models, and nonlinear models have extra texture because they even more spectacularly, the whole is not just behavior of the whole is not just directly predicated on the behavior of the parts in an obvious way. We have to simulate the model to understand the behavior. We can't predict it ahead of time in general, and we can get its response. So if we care about, and this is really where it gets very practical, if we want to change something in a fundamental way, if we want to improve something, with a nonlinear model it's trickier. Because with a nonlinear model, first of all, it may have many surprises associated with it, but secondly, when we think about how we can affect it to good change, to achieve good change, to most improved things, we can't even think about just evaluating it with respect to each possible type of change and then knowing how it responds to this type of change, that type of, say, vaccination versus faster treatment or something like that. We can't just analyze each in isolation. We have to analyze combinations of them. We can't say how it's just going to respond to A and respond to B and then assume we know how it responds to A and B. Not at all. Not at all. It's very different. We also will see situations where there's tipping points. What do I mean by tipping point? Can anyone say?
Small change as an input changes it automatically.
Dramatically, often in a qualitative fashion. So we'll see a situation where it's like night and day. And it can be just a function of a small difference. Now, the reason this is so exciting to us when we think about making changes to a system is that you may be able to, on the optimistic side, if you know how to intervene properly, you may be able to do so in a very artful way with just a little bit of an extra investment. Pays off hugely. You go from a situation where, your software project is constantly in chaos and, you're always struggling to deal with people who have left and hiring new people, and people, are because there's so many people leaving and coming, you have to go through very arduous documentation tests, and people's morale is low, and people aren't inspired to really do as much quality assurance, and the system is constantly fighting fires, reacting to challenges rather than being anticipating them, being proactive. In other words, it's constantly in turmoil and fighting fire mode. So much so it doesn't have time to prevent fires. You go from that to a situation where things are just humming along, very, very smooth. People's morale is high. Because morale is high, people are retained. Because people are retained, you don't have to do much documentation. Because documentation the job is somewhat more sort of enlivening. People have a very clear idea in their head of what's required, what someone else needs, and you have a situation where the team is, as they say, gelled. It's very effective. These are not make-up examples. I mean, you look at the software industry, you'll see gelled teams, you'll see non-gelled teams, you'll see teams constantly engaged in firefighting. It's like night and day. Same thing with infectious diseases. You go from a situation where a disease is, a disease like polio, or a disease like smallpox, or a disease like rubella. It's killing kids and causing great harm. And through artful investment, you can get it so that disease can't survive effectively in that population. So much so that even if someone were to come in with it, that it would quickly die out. Maybe they'd infect one or two people, but it would quickly get dealt with rather than spreading. So you go from a situation where it's like the movie The Thing, popping up all the time and infecting people, to a situation where you've got it well under control and kids aren't dying from this, and we're saving money as well because there's very little costs associated with it, etc. Night and day. There's many other examples like that too, pathogens and others. So with tipping points, we can get a qualitative change out through a little investment, an artfully chosen investment, judicious investment, and that can sometimes lead to huge benefits where you wouldn't have anticipated if you had just done a naive analysis. Now, on the negative side, what that means is that if we're not careful in using tools that will help alert us to these problems, we could end up in a situation where our project goes negative in a bad way, and we end up in one of those vicious cycles. We end up in a situation, low morale or what have you. We end up in a situation where smallpox roars back with vengeance, or more likely polio, and we're in really bad shape. So these models can help us kind of identify how do you deal most effectively, but judiciously, with these systems in a way that will allow us to achieve these dramatic gains, say for a small input. And how do we make it stable so that even if there's something punches us, there's something which occurs we didn't expect it, we're still robust, we're still resilient under that. That's what these models will allow us, clue us into, these opportunities to be resilient. Okay. So we're going to be going on to that in the next several lectures. It's how we can use these models for insight. And nonlinearity, folks, will have a lot to do with it. Okay. So I'm going to
Your computer with nonlinear situations.
that could be, although I'd have to think of the state variables involved to ponder that more. But I'm also aware of the fact that I'm at risk of reaching the tipping point unless I stop fairly soon. So if any of you have some fairly quick questions, I'm glad to deal with them now. But following that, I will repair to my home where I will seek the comfort of bed rest. And hopefully I, like the computer, will recover from adverse conditions in a dramatic way. And hopefully I'll have less dramatic a phase change in the middle. Okay? So thank you very much.